Now, ladies and gentlemen, please bear with me a little. I think if you guys have been using steel for some time, you should not forget about this. A shear lag factor is the factor that underlines the nature of the force transfer. Okay? It is like this. When you have a member, okay, this is the single angle, the angle that everybody knows. When we connect angle to the gusset plate or to the connection or to another member, whatever, chances are we cannot connect two elements, right? We can only connect one leg. So that means the force transfer will not go through the entire section, right? When the force which generally travels through the centroid of the cross section, can you believe that? And the centroid of the angle is in the air, is here. It's true. This is really, really funny, and you know, I have to share this story because it makes you believe in statics. Because the angle itself, if you draw the cross section, hang on a minute. Kind of left. Oh, we have a line on this side. We can come back to it. The angle, you know. Oops, that line's so bad. Here we have the angle. The centroid is here. So the centroid is in the air. What kind of section is that? That centroid is in the air. So that means if you even if you apply tension to the angle, it's going to bend. It doesn't matter whether you apply tension or compression. It's going to bend in the air. Because when you connect the angle to the support, you know, say this is the support, whatever that is. The force will have to travel from the centroid to the support. So that means if the force is here and it has to support, it has to go to the support. There is the moment arm or eccentricity. So it doesn't matter even if you apply tension. See, according to our own knowledge, tension is just the axial force, right? So how could you have the member bent under the axial force? It does bend because this axial force will have to travel. So the force itself will create moment at one time. And it's amazing that, wow, I believe in statics now. I got this because I tested the specimens with angle just to do something with the welds here in the research. Anyway, let's come back here. So when let's say if I connect this angle with the bolts or the welds, it doesn't matter. My force will coming through here, through the centroid, right? Oops, sorry. Just tell me, don't just give me the look like, what do you do, man? It's not on the screen. Just, please, it's not on screen. Just so that I know. You don't have to embarrass me. Okay, anyway, so the force comes in here. So that means the force is like water. And you cannot tell, hey, come here. Force, come here. Come to me. You can't do that, right? You're going to have to create the structure so that the force will just behave the way you want it to behave. So when the force comes in here, the problem is this. It's not going to go here, right? It doesn't want to because the connection is here, so the force would want to travel down here as quickly as possible so that it can get going anywhere, you know, to the support. So when it does this, this is the area where the force will not go. Right? So this area becomes ineffective in transferring the force. It's common sense, right? Why would the force want to go there? Because, hey, I calculate like this, so you should go there because I say so. It doesn't do that. You need to create the environment where it wants to go. So when your connection becomes very, very short, for example, say if I have only 2 bolts, so the force will come in fast and will want to go down like this. But then again, this area doesn't work. The force doesn't want to go to that area. So this area becomes ineffective. And you can see the ineffectiveness just comes in to the section where the rupture may occur. You see that? See this line? Okay, thank you. So you see, this is the line where the rupture should occur. But somehow the ineffectiveness of this member creeps into this line. So when the rupture is going to occur, the area that actually transfer the force is this much. It's not the entire area. If the force, if the rupture occurs here, maybe this is the A net, right? But this is no longer the A net because there's this area that becomes ineffective. So you are left with that area. So therefore this is UA net. So it makes sense. And it occurs when you have a short connection, and therefore the ineffective area just creeps into the area where the rupture may occur. And therefore, you don't have the entire net area to take care of the force when the rupture occurs. So that's why we need to reduce the net area by the shear lag factor. Yes, this is a failure under tension, but they call it shear lag factor, so don't ask me. I don't know why. They can just call it the flexural factor. I don't know. It's crazy. Anyway, so that's it. Now you have the means to calculate the shear lag factor. You can look from the table, which we will go back to that later on, but keep in mind that the shear lag factor generally occurs when you don't connect every element of the cross section. For example, in this example, we will only connect this leg. That leg will be in the air. So that is why the force transfer will not go into that area like this. Okay? All right, so it creates the ineffectiveness of the force transfer. If you can connect both legs, shear lag phenomenon will not occur. Never. But we don't need to try to, I have a gusset here, I'm just going to have a plate here so that I don't have shear lag. This is not practical. Okay, so we do it with one leg like this. We don't have that, but we're going to have to know how to take care of the shear lag, which is not the end of the world. Okay? Any question, ladies and gentlemen? Piece of cake now. Okay, so let's see. Shear lag will not occur if you connect every element in your cross section. Let's maybe go back to the slide, it will be better. Like this, for example. I can take this off, right? Somehow I don't do it. This, if you want to splice the edge shape, okay, because your tension member is very long, so you need to do the splice to connect two members. If you connect just the flange like this, so you don't connect the web, see, according to this picture. So that means the shear lag will occur because you leave the web like that. Now, if you choose to connect both the flanges and the web, this member will not have shear lag because the two flanges and the web are connected. So that means the transfer of tension in your member is complete. But again, we don't have to do that. If we don't do that, we're going to have to try to find a way to handle shear lag. If you have a channel like this, and you know the channel is very narrow here, the flange is very short, and it's also tapered. So to connect the flange here is very difficult. So we tend not to do it. So if you want to splice the channel, you only want to do it at the web. So you leave the flange out, the flanges out. So that means we don't connect the flanges, so shear lag occurs, right? So if you can find a way to connect at the connection through the web and the two flanges, shear lag will not occur. But shear lag is not the end of the world. We can handle it. And likewise here as well. And regardless of how you connect it, whether you use the bolts or whether you use the welds, shear lag will occur if you don't connect every element. So say, hey, I use the welds, I can just weld here, you don't have shear lag. No. It doesn't have anything to do with how you connect them. You need to connect every element so that you don't have shear lag. So like this, for example, if you weld through the leg, on both sides like this, but you don't weld through this leg, you still have shear lag. Okay? So now, the formula for calculating shear lag is pretty simple. It's just U equals 1 minus X bar over L. X bar is generally the distance that the force has to go or travel. In this case, as I just drew, the force is here at the centroid. So when it arrives at the connection, it has to go from the centroid to where the connection is, right? So that becomes the distance that the force needs to travel from the centroid of the member to the plane of the connection, right? The force is here at the centroid. And when the force comes to the connection, now the force needs to go through the connection to somewhere else. So it has to change the direction just like the car changing the lane from the centroid to this plane. So this is the distance that it has to travel. Okay? Which is, in fact, the property of your section. You cannot change that. Now, L is the length of the connection itself. See, for example, it begins from the first bolt to the last bolt here. And it's basically the length of the weld here, and you can use the average if the two legs are not equal. As you can see from the equation, 1 is 1, X bar is the property of the section, which you cannot change after the section has been selected. What you can change is the length of the connection. Now, if your L is small, this term becomes big, right? Because L is probably many people will not know these vocabularies. This part, this is called a fraction, right, in English. The upper part here is called the numerator. And that is called the denominator in English. It's crazy words, right? But now you know. So, okay. So L is the denominator. If it's small, the fraction becomes large. And so your shear lag factor is going to get smaller and smaller, smaller than 1. But if the denominator is large, this fraction becomes small. So your shear lag is going to get closer to 1. So the closer we get to 1, it means that we don't have the effect from the shear lag. So ladies and gentlemen, we can manage that by designing the connection long enough to avoid the shear lag problem. Easy, right? Yeah, of course. What else I want to say? Okay, there are two things that I always say. That is, the first thing is that long time ago, somebody included two numbers in. Is that 10:30 already? Oh, we have like 7 minutes. Come on. It looks like the real boss, right? Okay, so long time ago, some people included two magic numbers in shear lag. The first one is 0.9. This is based on the research, which was actually carried out by one of my committee members when I was doing my degree, Professor Easterling. He suggested that no matter what you calculate here, as long as you have shear lag, you should not use U greater than 0.9. It's just one number. Now this number has been removed from the spec, so I don't know. It's up to you. He only suggests that as long as you have shear lag, you should at least reduce the strength by 10%. That's just a suggestion. You can use engineering judgment on that, of course. Another one is, I believe, 0.65. Now, 0.65 is pretty low because let's say if you have U equal to 0.65, it means you already lose 1/3 of your strength, right? Without doing anything. That number would suggest that if you calculate the shear lag and you have U lower than 0.65, you should redesign your structure because you are losing too much. It's not efficient. Again, if you think, I don't care, I can use 0.5, what are you going to do to me? Nobody's going to do anything to you, sir, but you are just not being very efficient. That's all. Okay? Any question? I just realized that we have a screen on this side as well, so maybe it's a good idea to walk towards this side, right? So that we don't. Yes, please. You can ask in Thai. I'll translate that back into English. ถามภาษาไทยก็ได้ครับเดี๋ยวผมแปลเป็นภาษาอังกฤษอีกที So any question? Please, a question like, can we have a break now? You can just save it. He's going to do it for you. If the question is something like, can we have a break, please? I can't take this anymore. And things like that. Okay, anyway, I think we still have 5 minutes. And, okay, so let's revisit the, no, let's not revisit. Let's visit the table from AISE a little bit. This is the latest version. And you can see if you know, it's not easy for you to just go and read the table. That's why we are here together. So let me tell you this. The first case is that when you connect every element, so you have shear lag equal to 1. So just, why did I put it there? Just for the sake of completion, right? If they don't put it there, just, you know, you may think that you may not or may not have shear lag, but now they put it here and it's pretty clear that if you connect every element, no shear lag. If you don't connect every element, shear lag. If you, that's crazy. Now they have this formula. Yeah, that's the latest version. If you have the unequal wells like this, here is that. And I haven't done that myself. If you have the special connection like this, you know, gusset plate going through the tube section, use that. And if you have the square section, use that. If you have the two gussets like that, use that. If you're too lazy to calculate by using the simple formula that I just showed you, the 1 minus x bar over L, use those numbers. Okay? So, yeah, that's it for shear lag. And I guess so. If any question? You wanna? Yes.
In the building section, even you don't have hole in the member, so the larger failure is gonna occur before it.
No, it's going to occur after the yielding, right? Because if let's say we have the same area, the yielding will always come before the rupture. If the area is equal, right? So yes, when in terms of welding, you can say there's no need to really consider rupture. Yeah, because you're not gonna say it has already yielded. I'm just gonna let it go until rupture. You can't do that, right? You can't do that because let me give you another example. We all know that if we take the steel material to the lab, let's say you use SS400. Fy that you can use in design, in calculation, in inspection is always 2,500 kilogram per square centimeter. Even though if you test it, the number from the test is going to be something like 4,000. So the question is, somebody may ask you someday, hey, can I use 4,000? Because every time we test it, the yield strength is 4,000. So can we use it? No, because that's a design strength of SM400 material, right? When you test it and the number is greater than the specified number, it means you are safe. It doesn't mean that you can use it. Same thing. When you know that, okay, it may go on beyond yield, but in terms of engineering, we have to declare our structure unsafe and not fit for public use. Right. All right. Cheers. I think that's 10:30. So it's a nice spot that we leave for a break, I suppose. So how is everyone doing so far in English and everything? Piece of cake, right? Yeah, cool. All right. So that's time for a break. So this is already 10:30. All right. So we have a break. We come back for more. We are still in the we are still in the tension members, I suppose. And generally, when we think about the tension members, there's always something to do with the reaction due to the presence of the holes and so on. And we already mentioned the yielding of the member under the cross section. That's a pure force. And then we have the rupture of the net section when you have holes. And then introducing another failure mode. Now this time it is the combination of the failure under tension at this side and under shear at that side. And when this failure occurs, this chunk, this block is going to be torn apart from the member. So we call this failure a block shear, because this rate block will be sheared off from the member. Okay? Right now, I don't know if I should talk about this today or I should come back and mention about this tomorrow, because it's the design of the connection and the design of the tension member at the same time. So what do you think? Should I come back here tomorrow, or I should just go ahead and talk about this right away? By the way, that's a question, sir. Just go ahead, okay, a little bit. So yeah, you can see that this block can be sheared off from the member. So we need to approximate the force that will make this happen, okay? And right now, the design model of this failure is that they say this side, see, this is perpendicular to the force, right? Perpendicular means like this. So if it is perpendicular to the force, it is going to fail under tension. And this side is parallel to the force, so that means it is going to fail under shear, because it's parallel. And under this side, under tension, the failure that will occur will be tensile rupture. So when we calculate this, it is the ultimate strength multiplied by the net area under tension. So So the net area here means that you need to deduct the area lost to the hole. And according to this particular picture, the hole here and the failure line here is right here. So that means you deduct only half a hole, not one hole. Because the dotted line, red line, the failure line is coming in from this right to the center of the hole. So when you deduct the area is only half the hole. Okay? And the strength on this side is the ultimate tensile strength multiplied by the net area. We may talk about this UBS later on, but you can keep in mind that for the general member under tension, UBS is equal to 1. Okay? And now coming to this shear side, they say either of these failure can occur. The first is the shear rupture, and the shear strength is generally 0.6 FU. Okay? The 0.6 is the number that we use to relate the tensile strength of steel to shear strength. So we can safely say that the shear strength of steel is approximately 0.6 multiplied by the tensile strength. Okay, we may talk about this later on. A 0.6 is a magic number from a guy called von Mies. Yeah, von Mies criteria, whatever that is, yeah. So we multiply 0.6, we turn tensile strength into shear strength. So one mode is 0.6 FU multiplied by the net shear area here. So according to this particular picture, the shear area is this area deduct 2.5 holes. Okay, so that becomes the net shear area. And the design model is that we need to compare this shear rupture with the shear yielding. So when it comes to shear yielding, it means that it is 0.6 but Fy this time and multiply by the gross shear area, which is the entire area from this down to the center of the bolt hole here. We make a comparison and choose the smaller number between the two. Okay, so I can safely say now that the nominal strength of the block shear is equal to the tensile rupture on this side plus the minimum value between shear yielding and shear rupture on this shear plane. And that is a shear failure, block shear failure. Okay, and please keep in mind again that this is the nominal strength. That means when you use it for design or whatever purposes compare with the load, if it is LRFD, you need to multiply this by 0.75, and if it is ASD, you need to divide the number by 2. Why 0.75 and why 2? Because see, this is the rupture failure. Okay, it's one possible failure mode, and ladies and gentlemen, this can truly occur, especially when you have either a very short connection or a very thin connection. When this plate, the leg of the angle is so thin, block shear may occur before tensile yielding or tensile rupture. Or if this connection is very short, say you have only 2 holes, the shear area here becomes very, very small. So it can shear off before the tension will fail here, because when the tension is going to fail your structure, you have another leg here, right? So it is possible. Any question, ladies and gentlemen? Crystal clear? Or something close to it? Okay, so now move on to another one. This is the failure at each bolt hole. So you can always compare this to, when you have a piece of paper and you punch a hole in your piece of paper trying to put it in your binder, right? And your piece of paper may just, look like this, or like that, be torn off. So either one of them will occur. And when we talk about the steel plate, it is a very thin structure. So it can fail just like a piece of paper. If it is going to shrink like this, we call this failure bearing failure, because it is a failure under pressure. And we call that bearing failure. It fails under pressure. When you have two structures in contact, right? When you have two surfaces in contact, and one is stronger than the other, so one surface can push into another material. So it is shrunk like that, so, and creates what we call in English a wrinkle, right? So this is a bearing failure. And if this doesn't happen, another one may occur, and that is it's going to be sheared off, this entire block, and we call that tear out. And please, ladies and gentlemen, it's the same word. If you pronounce tear, it means you're crying, okay? And we don't lose tears here. This is tear, just the same spelling, different pronunciation. This is tear out, not tear out. If the tear is out, it means we are crying. And we're not crying, we're smiling, right? We're having fun. Okay. So here is the approximation. Right here is the bearing stress. And generally the bearing stress is 2.4 multiplied by Fu. It is very, very strong. So that means steel is very hard to fail under pressure. And the design strength itself is 2.4 Fu. Multiplied by this area, ladies and gentlemen, this is the projected area, which is equal to the diameter of the bolt multiplied by the thickness of the plate. So basically this failure is 2.4 Fu multiplied by the projected area, which is equal to dt. If you can see the picture clearly, I shall draw, because I love to draw. If I draw a hole, the projected area is this, right? And that dimension is d. And therefore then you have the plate thickness here. And that is the thickness of the plate, t. So this becomes the area, the projected area, and you have the area multiplied by the strength, which is equal to 2.4 Fu. All right? And now that we're on to the piece of paper, I may as well draw another failure here. If it is tear out, again we have the hole here, but the tear out failure is going to occur going out like that to the edge of the plate. So this becomes our failure area, right? But you have it on both sides. They don't look in the same line very much. Okay, okay, like this. And this is the area where the failure will occur. This is, see, the distance from the center line to the edge. And we call that LC. And so the area under failure is this LC multiplied again by the thickness of the plate T. You can again look from the picture in the slide in the book, but it's a bit small. It's the same. Now the shear strength is 0.6 Fu, right? The ultimate shear strength. But we have area on both sides, so instead of multiplying it here, you can multiply it here as well. Oops, okay, thank you. So when you multiply 0.6 Fu by 2, you have 1.2 Fu and then multiply by that area. So in comes the formula 1.2 Fu multiplied by LC and by T. Very easy, right? Just strength multiplied by the area which the failure may occur. So if you can see the failure, that means you understand the behavior and you can approximate the strength because there's no more than the area multiplied by the strength here. Any question, ladies and gentlemen? And we are in the mood. This LC may also be the length between each hole as well, you know. If you have a hole here, the LC becomes the distance between the center line of one hole to another. And if this is the edge of your metal, it becomes the distance from the center line of the bolt to the edge of the metal. All right. Drawing is always fun, right? It's like the only part that you can be sure that you can enjoy. Yes, sir. Okay. All right. Let's say 2.4 FU is in fact by itself the bearing strength of steel. 2.4 multiplied by FU, right? It's because this is not FU is the ultimate tensile strength, right? So if you want to tear the steel apart, the stress that occurs at the tearing is FU. But this is bearing. When you press the steel together, it's gonna fail when the stress reaches 2.4 FU because it's a pressure. So steel is very, very strong against pressure. So that's why the failure occurs at the stress equal to 2.4 multiplied by the ultimate tensile strength. It's a special number. Yeah, but it's just the strength, the bearing strength of steel. The number itself is a strength. And when we multiply by the area, it becomes a force. That's all.